Welcome to the Joy of Architecture. Today we're plunging into, well, the fascinating, sometimes frustrating world of how distributed services actually talk to each other.
Yeah, in cloud-native systems, microservices, it's a whole different ballgame than monoliths.
Right. In a monolith, it's all in memory, direct calls. Easy.
Too easy, maybe.
Yeah.
But yeah, you go distributed and bam, everything's over the network. Unreliable, slow, relatively speaking.
And that immediately throws you into things like those fallacies of distributed computing, doesn't it?
Exactly. Ascending the network's perfect, latency is 0, bandwidth infinite. None of that holds true.
And then there's CAP Theorem. Quick reminder for you listening. Consistency, availability, partition tolerance. Pick two, basically.
And since network partitions are going to happen with microservices...
You have to have partition tolerance.
Right. So you're forced into that trade-off, consistency or availability.
And that choice ripples through everything, especially communication.
Synchronous.
Asynchronous.
Yeah, the classic dilemma. Sync seems simpler, called
Right.
wait, get response, but it tightly couples services.
While async decouples things, but introduces its own headaches. Eventual consistency, delivery guarantees, stuff like that.
Which is exactly why we need these communication patterns we're discussing today.
Precisely. And you, our listener, send over a great collection of sources, articles, notes, research, all digging into these patterns.
So our mission today is to unpack those sources together, pull out the key insights, and help you navigate this complex landscape.
We'll start from the outside in edge patterns first, then service to service, asynchronous, and even migration stuff.
Sounds like a plan. Let's start at the edge. How do clients even get in?
Good question. The API Gateway, right?
That's the one. Think of it like the main entrance, the front door for all external requests.
So all traffic hits this gateway first.
Yep. And it's smart. It routes requests to the right internal microservice. It's not just passing things through blindly.
It abstracts away the internal messiness.
Exactly. The client just talks to the gateway. It doesn't need to know about all the individual services humming away behind the scenes. That really simplifies client development.
I can see that, especially for, say, a mobile app needing data from 3 different services for one screen.
Perfect example. The gateway can handle that. It aggregates requests. The client makes one call.
The gateway fans out, talks to the user service, the product service, the order service.
Collects all the answers, maybe transforms them a bit, and sends back one combined response. Reduces that network chattiness massively.
Which is great for performance, especially over flaky mobile networks.
Definitely. And it's a natural place for centralizing other things, too.
Like what? Security stuff?
Absolutely. Cross-cutting concerns. Authentication, authorization, rate limiting, caching. Handle it once at the gateway instead of in every single service.
Huge win for consistency. And security, I imagine.
Big time. You can terminate TLS there, enforce auth policies, integrate a web application firewall, or WA. It's a single choke point to lock down.
Okay, sounds powerful. What are the catches, the trade-offs?
Well, it is another piece of infrastructure. More complexity to manage, scale, keep highly available.
So it could become a single point of failure if you're not careful.
It could, yeah. Needs to be designed for high availability. And it adds a little latency and extra network hop for every request.
Makes sense. I'm picturing that flow. Client desk to gateway desk to client, that extra step.
Right. And observability at that gateway is crucial.
Because you see all the traffic.
Exactly. It's a gold mine. Request rates, error rates, latency.
Yeah.
It's all there. Plus, it's the perfect spot to start distributed tracing. Tag requests with an ID.
So you can follow a request's journey through the whole system. What about, like, failures? If a backend service is slow or errors out, does the gateway handle retries?
Generally, it's better not to have the gateway do automatic retries for backend calls. Some platforms might offer it, but...
Why not? Seems convenient.
It can hide problems or cause weird downstream effects if not done carefully. Usually, the gateway has a timeout, like AWS API Gateway's 29 seconds. If the backend doesn't respond, the gateway gives up and tells the client.
So the client should retry.
Often, yes. Especially for transient network issues. The client can implement smarter logic, like exponential backoff with jitter wait longer between retries, randomize it slightly.
Got it. And the gateway protects the backend services too, like back pressure.
Yeah, through rate limiting.
Yeah.
If clients send too many requests, the gateway can push back with the 429 too many requests status code. Protects the upstream services from getting overwhelmed.
And what if a backend service changes its API? Schema evolution.
The gateway is pivotal there. It handles versioning routing V1 requests to one backend, V2 to another. It can even transform responses, making a new backend look like the old one for older clients.
So keep it lightweight, focus on those cross-cutting concerns, Use declarative configuration, build in observability, and don't let it become a bloated monolith itself.
Nailed it. Companies like Netflix with Zool, ANZ Bank using Kong, the UK's DVLA on AWS, they demonstrate this pattern working at massive scale.
Okay, building on that. Backend for Frontends, or BFF. I like the name.
Yeah. It's a refinement, a specialized gateway. Instead of one big gateway for everyone,
You have multiple smaller ones.
kind of. You have a dedicated backend service for each distinct front-end experience. A mobile BFF, a web BFF, maybe one for IoT devices.
Tailored specifically for that client's needs. Why not just use the main gateway?
Because different front ends have very different requirements. Mobile needs lean, optimized payloads. Web can handle more data, maybe different formats. A single gateway trying to serve everyone often leads to compromises overfetching or underfetching data.
So the BFF delivers exactly what its front end needs.
Precisely. And it often gives the front end team more ownership.
The team building the web app also builds the web BFF.
Often, yeah. That boosts autonomy. They can evolve their specific API endpoint faster without waiting on a central gateway team or impacting other front ends.
Makes sense. Any other benefits? Security.
For web apps, yes. The BFF can handle the complex OAuth dance server-side, manage tokens securely using HTTP-only cookies. It provides a stronger security posture against things like cross-site scripting, XSS.
Okay, but now you have multiple BFFs. What's the downside there?
The big one is potential code duplication. If the mobile BFF and the web BFF both need to call the same core product service, that calling logic might get replicated.
Right, and just more moving parts.
More services to build, deploy, monitor, manage, increased operational overhead. And there's a risk, a temptation, to put business logic in the BFF.
Instead of keeping it in the core domain services.
Exactly. You have to be disciplined to avoid the BFF becoming a dumping ground, potentially leading to a sort of distributed monolith.
So, trade-offs again. Optimized experience and team speed versus duplication and operational cost.
It's always trade-offs. Operationally, each BFF needs its own monitoring. And distributed tracing becomes even more critical to see the full path. Client-BFF-downstream service 1, downstream service 2.
Resilience. Retries. Circuit breakers.
The BFF is the perfect place for that logic for the calls it makes downstream. It shields the front end from back-end failures. It can implement retries, back off, circuit breakers tailored to the services it depends on.
Okay, best practices. One BFF per experience, front-end team owns it. Keep business logic out, use shared libraries maybe, to cut down duplication.
That's the gist. Avoid making it a giant gateway for too many different clients and don't let it suck in domain logic.
Companies like SoundCloud, Netflix, Decathlon, they've used this.
Yeah, showing the benefits for tailoring experiences, especially across diverse devices. Though, as SoundCloud found, you need a strategy for shared concerns like auth to avoid re-implementing it everywhere.
Right, so that's the edge covered. Let's move inside the system. Service-to-service communication. Service mesh comes up a lot here.
Ah, yes, the service mesh. It's quite a concept. Think of it as a dedicated layer of infrastructure specifically for managing how services talk to each other.
Dedicated infrastructure, so it's not part of the application code itself.
Correct. It aims to handle things like secure communication, retries, load balancing, monitoring, transparently, outside of your service's business logic.
Transparently. How does it do that? Magic.
Close. It typically uses the Sidecar pattern. A small, lightweight proxy process runs alongside each instance of your service, usually in the same container pod or VM.
A sidecar. Like a little helper container.
Exactly. All network traffic going into or out of your main application container is intercepted and routed through this Sidecar proxy.
So my app just talks to localhost, and the sidecar handles the actual network stuff, like finding the other service, encrypting the traffic, maybe retrying if it failed.
Precisely. Your application code becomes simpler. It doesn't need to worry about those network complexities. The collection of all these sidecar proxies is called the data plane.
Okay, so the proxies do the work. Is there something controlling them?
Yes, that's the control plane. It's a central set of services that configures all the sidecar proxies, pushing down policies for routing, security, retries, etc. The control plane itself isn't usually in the request path, so it doesn't add latency to calls.
What's the big payoff for adding this whole mesh layer?
Observability is a massive one. Because all traffic flows through the proxies, the mesh can automatically generate detailed metrics, latency, request volume, error rates, the golden signals, plus logs and distributed traces, all without you instrumenting your code heavily.
Automatic telemetry. That's pretty cool. What
Well,
else?
security. Meshes often provide automatic mutual TLS or MTLS.
Mutual TLS.
Yeah, where both the client service and the server service automatically verify each other's identities using certificates before communicating. It provides strong, encrypted, authenticated communication between all your services, often with just configuration, no code changes.
Wow. Automatic encryption and auth everywhere. Powerful stuff.
It really is. Plus, standardized reliability features retries, timeouts, circuit breakers configured centrally and applied consistently, and sophisticated traffic management for safer deployments, canary releases, A/B testing, traffic splitting.
Okay, it sounds amazing, but
Yeah.
I sense a but coming. What's the con?
Yeah. Complexity is the big one. A service mesh is a complex distributed system in itself. Deploying it, managing it, understanding it, it's a significant operational undertaking.
And resources. Those sidecars must use CPU and memory.
They do. Every instance of your application gets a sidecar, so there's resource overhead. And there is a bit of added latency because requests now go through two proxies, the caller's sidecar and the receiver's sidecar.
So you're trading application code simplicity for infrastructure complexity and some performance overhead.
That's the core trade-off. For organizations with lots of microservices where standardizing security, reliability, and observability is critical, it can be a huge win. Think Istio, Linkerd, cloud offerings like AWS App Mesh.
And companies are really using this.
Oh, yeah. Xbox Cloud Gaming uses Linkerd for scale and deployment safety. Plaid uses it for simplifying MTLS across their services. It solves real problems at scale.
You mentioned the sidecar pattern is central to the mesh. Can we just zoom in on that pattern itself for a moment?
Yeah. Sure. The sidecar pattern is more general than just service meshes, especially popular in Kubernetes. It's simply deploying an auxiliary container right next to your main application container within the same pod.
And they share things. Network, storage.
Exactly. Same network namespace, so they can talk over localhost, often shared storage volumes, and they get scheduled together, live and die together.
The value is offloading those non-core tasks.
Precisely. Let the main application focus purely on business logic. The sidecar handles adjacent concerns. We saw network proxies and meshes. Other common uses are log aggregation. A sidecar reads log files from a shared volume and forwards them to a central system like Elasticsearch or Splunk.
Or maybe fetching configuration.
Yeah.
Or handling authentication.
Yep. Config injectors, auth proxies. Lots of uses. It promotes separation of concerns, keeps the main app cleaner, and the sidecar can be written in any language, reused across different applications.
Benefits sound good. Cleaner code, reusability. Trade-offs are similar to the mesh context.
Pretty much. Increased resource usage, CPU memory for the sidecar, a tiny bit of latency for the inter-process communication over localhost, and more containers to manage per application deployment. Lifecycle coordination used to be trickier in older Kubernetes, but recent versions handle startup shutdown order better.
So, a useful pattern for separating helper tasks. Single responsibility is key. Keep them lightweight.
Spot on. Don't turn the sidecar into another complex application itself.
Okay, and related to the sidecar, the ambassador pattern. Sounds diplomatic.
Ahaha. It kind of is. It's a specialized type of sidecar. Its job is to proxy outbound communication from your application to the outside world, external services, legacy systems, third-party APIs.
So not for service-to-service calls within my system, but for calls leaving my system.
Generally, yes. Think of it as your service's ambassador when dealing with external or potentially complex remote systems. The main app talks to the local ambassador sidecar.
And the ambassador handles the messy details of talking to that external thing, like finding it, retrying, maybe specific security protocols.
Exactly. It abstracts away that external network complexity. Maybe the external service needs specific retry logic or a particular authentication method, or maybe it's an old system speaking a different protocol. The ambassador handles that translation or interaction logic.
So the benefits are similar. Again, cleaner app code, language-agnostic features like resilience or security for those outbound calls.
Right. And it can help centralize how your services interact with a particular external system. Good for managing connections, maybe enforcing policies, especially useful when modernizing and integrating with legacy stuff.
Trade-offs sound familiar too.
Yeah.
Latency, resource overhead.
Yep, the standard sidecar costs apply. Operationally, you need to configure it carefully for the target system and monitor its outbound performance and reliability.
Best practice seems to be keeping it co-located with the client service that needs it. Don't make it a massive central outbound proxy for everyone.
Correct. It's meant to be a local helper for specific external interactions.
Got it. Sidecar for helper tasks. Ambassador as a specialized sidecar for outbound calls. Okay, let's completely switch gears now. Away from request response.
To the world of asynchronous communication.
Event-driven architecture. EDA. Publish, subscribe, pub/sub. This feels like where the real decoupling happens.
It really is. In EDA, services don't call each other directly. Instead, they react to events. An event is just a notification that something significant happened, like order placed or inventory updated.
So a service does something and it just announces it.
Pretty much. It publishes an event, often to a central event router or message broker, without knowing or caring who might be listening.
And other services can choose to listen.
Exactly. Consumers subscribe to the types of events they're interested in. When an event they care about occurs, the broker delivers it to them and they react accordingly.
Like shouting news in a town square versus making a phone call. Anyone interested can hear the news.
That's a great analogy. The primary benefit is incredibly loose coupling. Services don't need direct knowledge of each other. They only need to know about the events and the broker.
Which must be great for scalability and resilience.
Huge improvements. The broker acts as a buffer. If a consumer is down, messages can queue up. Producers aren't blocked. It prevents cascading failures. One service failing doesn't bring down others waiting on its response. Allows independent scaling. Plus, you often get better real-time responsiveness.
The freedom sounds amazing.
Hmm.
But how do you manage complex processes that involve multiple steps across different services if they're only reacting to events? Seems chaotic.
That's where we get into workflow coordination strategies, often discussed in the context of the Saga pattern for managing distributed transactions. The two main approaches are choreography and orchestration.
Choreography sounds like a dance.
It is. It's the decentralized approach. Each service listens for events it cares about, does its work, and publishes its own events. The overall process emerges from these independent reactions.
Like that e-commerce example. Order service publishes order placed. Payment service listens, processes payment, publishes payment processed. Inventory service listens to order placed, reserves stock, publishes inventory reserved.
Exactly. And then maybe a shipping service listens for both payment processed and inventory reserved before it initiates shipping. There's no central boss telling everyone what to do.
Benefits of that.
Yeah.
Super decoupled, right? Scalable.
Very much so. High economy for services. But the downside is visibility. It can be hard to see the whole end-to-end process, hard to debug when things go wrong because the logic is spread out, and you have to watch out for creating accidental cycles.
Okay, so what's the alternative? Orchestration.
Right. This involves a central orchestrator component. Think of it like a conductor leading an orchestra. It explicitly tells each service what to do and when.
So like for user signup, orchestrator calls user service to create user. If successful, it calls email service to send verification. If user service fails, it stops. If email service fails, maybe it triggers a compensating action.
Precisely. The orchestrator manages the flow, state, error handling, and compensating transactions, actions to undo previous steps if a later step fails.
The benefit there seems to be much better visibility and control.
Definitely. The workflow logic is explicit and centralized, easier to understand, monitor, and manage complex error scenarios. The trade-off is tighter coupling services become dependent on the orchestrator, and the orchestrator itself can become a bottleneck or single point of failure if not designed well.
And you risk that smart orchestrator, dumb services problem.
Yeah, where too much business logic ends up in the orchestrator instead of the domain services. So often the advice is use choreography for looser coupling between major business domains, bounded context, and maybe orchestration for complex workflows within a single domain where control is paramount.
Makes sense. Maybe even a hybrid approach sometimes.
Very common in practice.
Okay, back to ED fundamentals. Yeah. Besides workflow, what are the other big challenges?
Eventual consistency is inherent. Since updates propagate via events asynchronously, different services might see slightly different states of the world for brief periods. You have to design for that.
Not always seeing the absolute latest data immediately.
Right. Guaranteed ordering can also be tricky. Brokers like Kafka guarantee order within a partition. Events with the same key arrive in order, but not necessarily global order across all events. Debugging is inherently harder, too, tracing requests across async boundaries.
And handling errors. If a consumer service fails to process an event.
That needs careful thought. You need robust retry mechanisms, usually with exponential backoff. And crucially, a way to handle messages that consistently fail the poison pills. That's what dead letter queues, DLQs are for. Failed messages get moved there for later inspection, preventing them from blocking the main queue.
So you don't get stuck retrying forever.
Exactly. And consumers need to be idempotent.
Idempotent,
Yeah.
meaning processing the same message twice doesn't cause problems.
Correct. Because many messaging systems offer at least once delivery guarantees, a consumer might occasionally receive the same message more than once. It needs to handle that gracefully, perhaps by checking if it's already processed that specific event ID.
Got it. Operationally, observability sounds tough.
It is. Distributed tracing is vital, but you need to make sure correlation IDs are passed along within the event headers or payload to link things together. Centralized logging is key. And monitoring the broker itself, queue depths, message lag, throughput is essential.
Schema evolution too, right? If the structure of an event changes.
Huge challenge. Producers and consumers need to agree. Using a schema registry, like Confluence for Kafka, helps manage event schemas and enforce compatibility rules. Example, allowing additive changes but not breaking ones.
So best practices. Clear event contracts, maybe using Avro or Protobuf.
Right.
Design identity consumers, keep events focused, avoid fat events with tons of data, use correlation IDs, and don't try to mimic request response over messaging.
You got it. Examples like Netflix, Uber, financial giants, they leverage Kafka, RabbitMQ, or cloud services like EventBridge or PubSub to handle immense event volumes, showing the power of EDA for decoupling and scale.
Let's briefly touch on the message broker itself. It's the enabling tech here.
Right. The broker is the software that acts as that intermediary. It receives messages, stores them reliably, usually, and delivers them to interested consumers. It's the heart of many EDA systems.
Providing that decoupling, temporal decoupling, sender receiver don't need to be online simultaneously, and location transparency.
Exactly. And it supports both main models, publish, subscribe, using topics for broadcasting to many, and point-to-point, using queues where typically only one consumer processes each message.
Queues for work distribution, topics for notifications.
Generally, yes. The benefits are reliability, messages persist, asynchronous flow, load balancing, brokers buffer spikes, and independent scaling.
Downsides. The broker itself.
Can be a single point of failure if not clustered or replicated properly. Adds operational overhead, another complex system to manage, introduces some latency, and you do become somewhat coupled to your chosen messaging technology.
We mentioned Kafka, RabbitMQ, ActiveMQ, cloud options like SQSSNS, Azure Service Bus, Google PubSub. They all fit here.
Yep, each with different strengths. Kafka is like a distributed log, great for high-throughput streaming and event replay. RabbitMQ is more traditional, very flexible routing, good for task queues. Operationally, high availability is non-negotiable. Monitoring queue depths, unbounded queues are dangerous. Message throughput, latency, all critical. And again, DLQs and idempotent consumers are essential practices.
But we've hit edge, internal sync, internal async. What about the elephant in the room for many organizations? The monolith. How do you integrate with or migrate away from that?
Migration patterns. The Strangler Fig pattern, coined by Martin Fowler, is a key one here.
Strangler Fig, like the vine that eventually overtakes a tree.
That's the metaphor. The idea is incremental migration. You put a facade, typically an API gateway or a smart proxy, in front of the monolith.
Okay, so traffic flows through the facade first.
Right. Then you identify a piece of functionality in the monolith, build it as a new separate microservice, and configure the facade to route traffic for that specific functionality to the new service. Everything else still goes to the monolith.
And you repeat that. Carve off another piece, build a service, update the routing.
Exactly. Over time, more and more traffic goes to the new microservices and less goes to the monolith. Eventually, the monolith handles little or no traffic and can be strangled, decommissioned.
That sounds way less terrifying than a big bang rewrite where you try to replace everything at once.
That's the main benefit.
Yeah.
Drastically reduced risk. You deliver value incrementally as new services come online. You can often do it with zero downtime because the old system stays running. And you learn and adapt your approach as you go.
Makes sense. What are the really hard parts of doing this?
Managing the transition phase is complex. You're running two systems side by side. Data synchronization is often the biggest hurdle.
How does the new microservice get the data it needs if it's still living in the monolith's giant database? Or if it needs to update data used by the monolith?
Big challenge. You might need temporary two-way data sync mechanisms, or use change data capture (CDC) tools to stream changes from the monolith's database logs to the new services. Sometimes new services might write data back to the monolith via APIs initially.
And untangling the monolith's internal code must be tough too.
Very. Often, a newly extracted service still needs to call back into the remaining parts of the monolith for data or functionality you haven't migrated yet. This usually requires creating an anti-corruption layer, ACL.
An ACL, what's that?
It's basically a translation layer. It sits between the new microservice and the legacy monolith code. It translates data models and interactions, protecting the clean design of your new service from the complexities or outdated models of the legacy system. It prevents the corruption from leaking out.
So the facade routes traffic, CDC or other methods handle data sync, and the ACL manages interactions between the new world and the old world during the transition.
That's a good summary. The Strangler Fig is really a strategic approach implemented using these tactical tools like gateways, proxies, CDC, and ACLs. You won't always find flashy case studies explicitly named Strangler Fig, but most successful large-scale incremental monolith migrations implicitly use these principles.
Wow. Okay, we have really journeyed through a wide spectrum of patterns today,
We sure have, from the edge with API gateways and BFFs,
to internal communication with service meshes, sidecars, ambassadors.
then shifting to asynchronous with EDA, PubSub, message brokers, and figuring out choreography versus orchestration.
And finally, tackling legacy systems with the Strangler Fig. It's a lot.
It is a comprehensive toolkit, and I think the recurring theme from all the source material we looked at is there's no single silver bullet.
Right. It always depends on the specific context, the specific problem you're solving.
Exactly. You're constantly balancing those benefits, decoupling scalability, resilience against the trade-offs, complexity, operational overhead, maybe consistency guarantees.
Understanding these patterns gives you, the listener, the vocabulary and the options. It helps you make informed architectural decisions when facing those inevitable distributed system challenges.
Which brings us to a final thought, maybe something for you to chew on. As patterns like service mesh become more mature, as serverless platforms handle more eventing infrastructure, are we abstracting away the complexity of distributed communication?
Or are we just pushing it, moving it from the application code into the infrastructure layer? Or maybe just changing the kind of complexity developers and ops teams need to understand?
Is it truly simpler or just different? Something to ponder.
A really interesting point. Well, thank you for joining us on this deep dive into integration and communication patterns. We hope exploring these sources was valuable for navigating your own architectural puzzles.
Absolutely. Stay curious, keep building, and join us next time. Remember to subscribe to Joy of Architecture for future deep dives.